Now, this film isn't going to be about guns and bullets. It's just that in the last few lessons, we pictured light as if it were a stream of bullets. We found out that to a certain extent, light does behave at least as if it were a stream of particles of some sort. Remember that reflection and refraction, the fact that light moves in straight lines, all seem to fall into place. It's true we've had to make a few extra assumptions here and there, but the picture isn't too bad. Today we'll try to reverse this. Let's take something that the theory suggests, something we know about bullets, and see if it's true about light. What happens when you shoot at a tin can? The bullet doesn't just stop and fall to the ground. For a short time, it exerts an impulse. Now, if light behaves like a stream of bullets, it ought to do something of the same sort. It's not going to send a tin can flying off, but it ought to exert a little push. Let me say it this way. For a theory to be any good, it has to work two ways. It, first of all, has to sum up the things you know, and then it ought to suggest some new experiments to try. So today, we're going to look for the pressure exerted by light. People tried to find this more than 150 years ago, but it wasn't until early in this century that some experiments were worked out that convinced us that we had really seen the pressure of light. Let's try the simplest experiment. I'm going to balance this little mirror on edge and shine the light of a 20-watt automobile spotlight on it. You can see right there the light reflected onto the table, and it doesn't fall over at all. Whereas, if I blow on it just a little bit, over it goes. You weren't in the least surprised at that, because you knew perfectly well that if you turn on the lights in a room, you're not pushed back against the wall, and if you walk out into the sunlight, you don't feel anything pushing on you. You feel a little heat, to be sure, but nothing pushing. So the pressure of light is going to be a little harder to find than that. Let's talk about a more refined experiment. Look at this little pinwheel that I bought at a local drugstore. It's going around in the light of the studio here, and I'll stop it so that you can see it. In fact, I'll do a little better than that. Look here. Here's one I broke apart, and you'll observe that the veins are black on one side and shiny on the other, and that it turns because there's a little, that's soot, there's a little needle point bearing there, and to be sure it's blowing around, it has to be encased, and as a matter of fact, it has to be evacuated in order to do that, and the pressure in there is only about 1/1,000,000th of an atmosphere. It was invented more than 100 years ago by Sir William Crookes in order to demonstrate the pressure of light. We call it now the Crookes radiometer. Let's take a look at how Crookes reasoned this thing out. Here is the needle point bearing there, and here are the 4 veins, and here are the sooty sides, like that. Now, Crookes said that if a particle of light hit here, on the black side it would be absorbed, whereas if a particle of light hit here and is reflected back, there would be a larger push on this side than on this side. We can measure this effect. Here's an ordinary steel plate hung from a wire so that it swings this way. And at the top of this steel plate on this side, I have a little axle grease to act as an absorber for bullets. And the bottom of the steel plate is clean, so it's a reflector for bullets. Let's try a very simple experiment of comparing what happens to the turning of that steel plate when I hit the grease and when I hit the plain steel, and it's reflected. I'll first mark a 0. That's where the edge of this little marker is. Now I should hit the grease, and the little marker moves this far. So, and let's try now once more. Same size bullet. This time we'll hit the steel down at the bottom. And the marker moved almost twice as far. You can try that experiment yourself sometime. Just take a kitchen frying pan, maybe that big, a heavy iron frying pan, and instead of using that axle grease, use a little butter. It's easier to wash off, and any kind of thing like a pistol and ball. I think you'll find that if you do it repeatedly, that the push that the plate got when it reflected the ball back was twice as big as the push it got when it absorbed it. And that is what Sir William Crookes thought was happening in the radiometer. Let's take a look at this. If light behaves like particles, it's going to exert twice as much force on the shiny side, that side, as it does on the black side where it's absorbed. And so it ought to go around. Let me put a good one there in the field of view. You can see it going around in the studio lights. And in fact, if I bring up my 20-watt lamp and shine it on it, it just whizzes around. But let's look at this a little more closely. According to our theory, the push should be greater on the shiny side than on the black side. There you see it going around, and it's going around with the black side trailing. So it's wrong. Something's the matter. Something doesn't add up. And that's exactly what Crookes thought when he invented this device. Now, nature isn't wrong. The theory's wrong. Instead of demonstrating the pressure of light, he must have been demonstrating something else. So Crookes, who had set out to solve one problem, ended up with two problems. He was convinced that light must exert a pressure, but clearly he hadn't proved it. And secondly, he now had to find out what made the pinwheel go backwards. A man named Sir Arthur Schuster reasoned that even though most of the air had been removed from the glass bulb, it was still the remaining gas inside, the gas inside, that was responsible for this funny misbehavior. He was able to prove this, and I think we can too. Let's take a look over here at what I choose to call a homemade radiometer. You'll see that we've tried to make something like the one you've seen just a moment ago. It's a little fancier than that. Over here is an electronic vacuum gauge. Down below is a pump. It's an electronic pump, too, made for this kind of operation. Just above it is a steel ball in a seat, so arranged that if I lift the steel ball out here and bring it over to this part of the glass tubing, it will open up the tube here and allow the pump to pull the gas out of the radiometer down into this region. Let's turn on the gauge. Can I have a little help? The gauge is beginning to read. Okay. The pressure reads about 4 millionths of an atmosphere. Now let me bring up my light again. You can see the vanes go round. Now let's see what happens if we try to improve the vacuum. I'll lift the ball valve out of its seat there. The vacuum is improving. I don't know how low it is, but it's pretty low. Now let's shine the light on it. And there the light is shining on that vane. It shines on this one. It shines on that one. But it certainly is not an effect. What we see there is that if there's no gas, there's no go. In other words, the Crookes radiometer is something that's working by gas pressure. And if we can see that the gas is needed to make the radiometer work at all, it must be the gas that's making it go backwards, at least backwards according to the theory. A complete explanation of this is pretty complicated, but I think we can understand it in some kind of way like this. Suppose we picture the radiometer as we did before, with the sooty sides, the black sides here. So, now, the gas molecules hit black sides and hit shiny sides. The effect of the light is to warm up the black side more than it does the shiny side, so that a molecule that comes down here and hits this and then goes away again goes a little faster than a similar one coming at the vane from this side going this way. The recoil, therefore, is greater, and that means that the push is predominantly on the black side. In other words, it should move from the gas inside the vessel with the black side trailing. And that's, in fact, exactly what the radiometer does. So we come to another question. The other question is, has the radiometer failed to move because there is no pressure of light, or has the radiometer failed us because friction at the bearing or something of this sort? To find out, let's use a more delicate piece of apparatus than any we've used so far. Here we have one made specially for this purpose. Supported from the top is a very thin fiber drawn from molten quartz. It's about 1/10 the diameter of a human hair. You might be able to see it jiggling in there. I just barely can see it. Suspended from the end of it, right down here, is a small piece of aluminum foil cut from a kitchen foil, thin kitchen foil. It's just hanging from the bottom there. And down here is another one of those electronic pumps that keeps this vessel, this piece of glassware, evacuated better than anything that we used before. Now, you'll see that this experiment is specifically designed to get rid of the effects that were interfering with the others. We get rid of the friction by suspending a light vane on a very fine thread. We get rid of the trouble caused by the gas in actually 3 ways. First, the vane is so thin that the temperature will equalize on both sides in a very short time. It's as hot on one side as it is on the other. Second, the vane is shiny on both sides, so there won't be any uneven heating. And then third, and of course most important, the vacuum is so good that the effect of the residual gas is really completely negligible. The calculation of that effect is in the film notes. It's a little laborious to go through right here. Now let's try the experiment. I'll pick up our old friend, this lamp, and carefully shine that on one side, and you don't see anything much happening. Well, it moved a little bit, but it's not very convincing. Let's try another trick. Let me shine this light first right there. And when it's swinging away, I'll shine it again. There. I'll shine it on that side again. Once more. I'm pushing always on this side when it's swinging away. You heard me say I'm pushing. I shine the light on this side, and the light's doing the pushing. There are not many people in the world who've seen that thing and know that they've seen the pressure of light for sure. It's a small effect, but there it is. Now, this is not just an experiment to see whether the pressure of light exists. We can also measure the pressure of light this way. If you measure the time of the swings, that is, the number of pushes you have to make to swing it up to a certain amplitude, and if you know the mass and size of that little vane there, you can calculate the pressure of light quite directly. And if you do it with this particular apparatus, you get one which is in a quite good agreement with everyone else's determination of about 10 to the minus 9th atmospheres from that 20-watt lamp. Now, that's a fairly small pressure. On the other hand, you may want to know, how does that compare with other light intensities that you're used to? If you walk out into sunlight, the pressure is about 1/30th of that. It's about 3 times 10 to the minus 11 atmospheres. The reason our pressure is larger than the one in sunlight is because we've concentrated that light with a lens so that, in fact, it almost burns my finger. It's only natural now to ask whether something that's as small an effect as that has any role in the universe. The tail of every comet, for example, streams away from the sun. It doesn't follow the comet. And it was just this effect that suggested to Kepler, as early as 1619, that light had pressure, and he began to look for it. How much of this is actually due to light pressure and how much is due to other effects like streams of other particles, we don't exactly know yet. The astronomers don't quite agree. But light pressure plays a part. But it plays an even greater part, and this for certain, in the stars. It's the pressure of light that keeps many of them as large as they are. You'll find the detail of this in the film notes. Now, if you'll pardon my being a little corny here, I'd like to say it this way. Here we've seen something which was almost completely trivial. We had to make a very fancy apparatus to see it. Nonetheless, it is one of the major building blocks of the universe. It keeps the stars, and that's where most of the mass is, it keeps the stars out to the size that they are. Now, let's review a little what we've done. We've had a theory that light was a stream of particles, sort of like bullets. We know that when bullets strike an object, they exert a momentary force. And so we reasoned that if the bullet theory of light is a good one, then a beam of light should push on any object that it strikes. And then, after some difficulties, we found that light does exert a force, and so the bullet theory does indeed predict the correct behavior of light. Now, what have we done? We've given strength to the bullet theory, but we haven't proved the bullet theory. In fact, we're going to find presently that a wave theory of light also predicts a pressure. But more of that later on.